All right, welcome to Math 153. These videos are meant to supplement your readings from the book Full Frontal Calculus, not to replace them. I'm going to use these videos to offer some slightly different or slightly expanded explanations from the book and to provide some further specific examples, the sorts of things you would see in a good old-fashioned classroom lecture. I'm going to assume that when you watch these videos, you've already read the assigned sections from the book. I am not, however, going to assume that you have mastered the material therein. I hope the videos will help fill in some of the gaps in your understanding so that when you return to the book, it will make that much more sense to you. But I don't want to waste any more time with introductory nonsense, so let's just jump right in. The first topic in Chapter 7, which is where we begin the class, is Taylor polynomials. These things are fascinating, as I hope you've already seen by reading the section, but rather than jumping straight into Taylor polynomials, what I want to do is back up and expand on an idea that I used to motivate them in the book. In the book, the motivation was to talk about how your calculator goes about giving you approximations to things like sine of 22 degrees or whatever it might be. And if you haven't really thought about it much, it may be hard to appreciate what the problem really is in the first place. So let's back away even from that problem and start with something much simpler. What's 312 times 87? Well, you know how to figure this out. If you were trapped on a desert island and you didn't have a calculator, you would do the usual thing. Well, let's see, 7 times 2, that's 14, that's 7, that's 8, that's 21, that's 16, so that's 8, that's 9, that's 24. I hope I didn't make an arithmetic mistake anywhere, and I think it's 27,144. Yes, I know, Calculus 3 is beginning to look like third grade math or whatever that is, but it's worth going back to elementary school for a minute. Just to remember that, yes, we know how to do that. And when we stick that into our calculator and we get that out immediately, it's purely a labor-saving device. It saves us time, and the machine is less likely to make a mistake somewhere doing arithmetic than we are. So we're very grateful to Texas Instruments or Casio or whatever it is that we use. But we do know how to do it. And most of us would like to think that when we use a calculator, that's all we're doing with it. We're really just letting the machine automate things that we could do on our own, but we'd rather spend our time doing something else. And as long as that's what we're doing, well, that's great. But we do want to be able to know that we could, in principle, come up with the answers on our own, and that we're not relying on these machines to do things we don't understand. Let's take a slightly more subtle example. What if we wanted to get an approximation to, say, the cube root of 7? Now, unlike the multiplication example we did a moment ago, this probably isn't something you learned in school, how to actually come up with a numerical approximation for that. And that's fine. But even though you were never taught an explicit method for doing that, if you were trapped on a desert island somewhere, and under some bizarre set of circumstances, you had to come up with the cube root of 7 to 3 decimal places, you could still figure out how to do it. The reason you can do it is because this is defined arithmetically. It is defined through arithmetic. We just have to think, well, what does this mean? What is the cube root of 7? Well, that's the number that when you cube it, you get 7. And so by thinking about that definition, we could come up with it. For example, we know immediately that it's going to be bigger than 1, because if I cube 1, I don't come up with 7, I come up with 1, which is much lower than 7. On the other hand, the cube root of 7 is definitely less than 2, because the cube root of 7 is the number that when we cube it, we get 7. Whereas when we cube 2, we get 8. It's too big. So we have to play Goldilocks here. This one's too small, this one's too big. We're never going to find something that's just right, but we can squeeze these bounds closer and closer. I mean, we've already done pretty well. We've narrowed it down between 1 and 2, so that I know that the cube root of 7's decimal expansion begins 1 point something. What comes after this? What about 1.5? If I cube that, do I get something bigger than 7 or smaller? We could work it out. We could say, well, if you cube it, well, that's the same thing as squaring it and then multiplying it by 1.5. And you square it, well, let's see, 15 times 15 is 225, so that would be 2.25, and multiply by 1.5, that's like this, and half again, so that would be what? Half of that is 1.125, so I think it would be 3.375. Oh, well, that's way too small. We want the number that when you cube it, you get 7. This is the number that when you cube it, you only get 3.375. So I can improve that bound. In fact, the cube root of 7 is going to be greater than 1.5. So then I could say, I don't know, what about maybe 1.8? And I could cube that and get whatever I get. I don't want to waste my time doing it, but you get the point. You could figure it out sitting on that desert island. In fact, if you work it out, it turns out to be 5.832. So it's too small. So that means this thing is not just bigger than 1.5, it is bigger than 1.8. You could continue playing this game and try it with 1.9. And after scratching it out on the sand in your desert island, you'd say, that's 6.859. Still too small. That means the cube root of 7 must be bigger than 1.9 and smaller than 2. Hey, that's pretty good. I know that the decimal expansion must begin 1.9 something. Not bad. Well, what do you think I'd do next? I'd try maybe 1.95. And I'm not going to go any further, but you get the idea. You could whittle it down, bring this one up, bring this one down, and by playing this game for however long it takes, half an hour or something, you could come up with 3 decimal places of accuracy, 5 decimal places of accuracy, whatever it takes. Now, we all agree it's much, much nicer just to type that thing into your calculator, which I'll do right now, and boom, I see that it's about 1.912931183. It would have taken me an hour to come up with all those decimal places playing this ridiculous game right here. So we're very, very grateful to our calculators for doing that nasty work for us. And I should point out, this is not the most efficient way to come up with those decimal places. There are much, much, much better ways. But the important thing is we could do it. And we could do it because the cube root of 7 is defined through arithmetic. The number that when you cube it, you get 7. It just involves cubing, which is just multiplication. Okay, you get the point. But just to ram it home a little further, I'll give you one more example. Unfortunately, you wash up on another island, and the evil demon that controls that island won't let you go until you have found the value of log base 10 of 6. And you might fall to your knees in despair and say, oh my God, I have never computed something like that without a calculator in my life. How am I going to do it? Until you realize, wait, that's just defined through arithmetic as well. This stuff is just the power we have to raise 10 to get 6. We know it's certainly greater than 0, because if I raise 10 to the power of 0, I get 1. On the other hand, I also know it's less than 1, because if I raise 10 to the power of 1, I get 10. Okay, so that's a good start. Ooh, now it gets a little uglier, though. I might say, well, can I try? Maybe it's 0.5? But then I have to think, well, what happens when I raise 10 to the power of 0.5? Ew, that means the square root of 10. It's definitely less than the square root of 36, which is 6. And I'm looking for the power we raise 10 to actually get 6. So this power isn't high enough. Log base 10 of 6 must be greater than 0.5. So then you might say, what about, I don't know, 0.7? If I raise 10 to the power of 0.7, will that give me 6? And then you have to think, what the hell does that mean? Oh, that's 10 to the 7/10. My God, that's disgusting. That's the 10th root of 10 to the 7th. Yikes. And you've got your work cut out for you on that island. It's going to take a while to approximate this thing. But you can do it, as we talked about when we approximated the cube root of 7. It's the exact same process, it's just more tedious. And if you did this over hours and days or whatever it takes on that island, you could eventually come up with an approximation to log base 10 of 6. Now, thank God, you aren't going to end up in a situation like that, and you can always just turn to your calculator to approximate it, and it takes a second. Typing it into mine, I immediately find that this is about 0.77815,125 approximately, and I'm immensely grateful to my calculator that it came up with that. But the important thing here is not just to praise the calculator. The important thing is to recognize that this was defined through arithmetic. So we could, in principle, come up with an approximation to it on our own. It's just that we don't want to. We have better things to do with our time. And it would be nice to think that every time we turn to a calculator to get a decimal approximation, that's what we're doing. But that really isn't the case. So now let's go back to the kind of question I asked in the beginning. Sine of 22 degrees. Now I can't get off the desert island until I can approximate this to 3 decimal places. We might be feeling confident after the last two, but there's a big, big difference. This is not defined through arithmetic. What does it mean, sine of 22 degrees? You might say, oh, well, that's, I have a right triangle with a 22-degree angle in it. That's the ratio of the opposite side to the hypotenuse. And that's true, but if you set about on your desert island trying to draw a really accurate right triangle with a 22-degree angle, first of all, how are you going to do that? And second of all, you're not going to be able to measure it with that kind of accuracy that you're going to come up with that. You are out of luck. Sine is defined geometrically. It is not defined arithmetically. So a calculator which operates exclusively in terms of arithmetic has no idea what this function even could possibly mean. But nonetheless, if I punch this into my calculator, it tells me, oh, that's 0.374606593 and etc. What's it doing? In this case, unlike those other ones with the logarithm and the multiplication and the cube root, you might say, I don't even know in principle how we could come up with that. And worse, I don't even know how the calculator, you might say, could come up with that. And that's where the brilliance of Taylor polynomials comes in. The idea, to reiterate what's in the book, is that if we have the sine wave and we want to know its value at 22 degrees, the principle on which the calculator operates is this. It doesn't know what sine means. It just knows that if somebody presses sine, it thinks sine is a polynomial. It works with some polynomial, like maybe one that looks like this, that hugs the curve really, really closely near 22 degrees. And when you ask it for sine of 22, it just sticks 22 into that polynomial. And the polynomial is just arithmetic, because what's a polynomial? It's just a lot of multiplication and addition. So the calculator loves to do that kind of thing. It's great at addition, multiplication, and raising powers. It just doesn't know what sine is. So if it's programmed to use a polynomial that can fool us because it's so close to the value that the first 9 decimal places or so will coincide with sine's value, and everybody's happy. And more or less, that's what's happening when you ask your calculator to evaluate something like sine of 22 degrees. It's faking. But man, is it faking it well. So well that we don't even care. Now, our question is, what's going on? How do you come up with such a polynomial that approximates some non-polynomial? And that's, of course, what the section is about. Now that some of that motivation is out of the way, let's talk about Taylor polynomials in general. Not just for the sine function, but for any sufficiently nice function. So let's imagine we've got some general function f, and we want to come up with a Taylor polynomial, a polynomial that approximates this thing very well, at least in the neighborhood of some point where we anchor the Taylor polynomial. Now in the book, I initially anchored everything at 0. We did Taylor polynomials anchored at 0, so that it was a perfect match at 0 and close nearby, and then it differed as we went further away from 0. But here in the videos, let's be more general. We can center a Taylor polynomial anywhere we want. So let's just say we center it at some point A in the domain of our function. So we will be looking for a polynomial that matches our function at A. So it's actually going to go through that point, a f of a, and fits it really well in some neighborhood of a. So if we take any values of x to the right or left of a, the values of f in that neighborhood should be nearly indistinguishable from the values of our polynomial there. And of course, we recognize that the further we go away, well, it's going to start to tail off, and such is life. We don't care about that. We just wanted to approximate well nearby, near a. How do we find such a Taylor polynomial? Well, I discussed that in the book, how we come up with an explicit formula for a Taylor polynomial of whatever degree you like. But rather than deriving that, rederiving that all at once here, I just want to build it up step by step so that you get a feel maybe for why it works that way. And when I say step by step, I'll say degree by degree, because we get to choose the degree of the Taylor polynomial that we work with. And in practice, we often use first-degree Taylor polynomials, second-degree Taylor polynomials, third-degree Taylor polynomials, or whatever. But let's start with a silly case, a 0th degree Taylor polynomial. More specifically, what we want is the 0th degree Taylor polynomial for f, this function, centered at a, this particular point in the domain. Every word in that statement is important, including this article at the beginning, the. There is only one. This is unique. What is it? Well, first of all, it's a 0th degree polynomial. What the hell is a 0th degree polynomial? I mean, we know what a third degree polynomial or first degree, 0th degree polynomial is a constant function, like y equals 2 or y equals 7. If it's going to be a Taylor polynomial for f centered at a, the Taylor polynomial for f centered at a, that means it's going to match the function at a, so it's going to pass through that point, and of all 0 degree polynomials that do so, the Taylor polynomial is going to be the one that approximates this function in a neighborhood of a as closely as possible. Well, what's that going to look like? Is it going to be this one? No. Is it going to be this one? No. There's only one choice here. It has to be this one, the horizontal line that actually passes through that point. So what's it going to be? Y equals 7, y equals 9. Well, it's y equals whatever this value is. Y equals f of a. So I'll put that up here. The 0th degree Taylor polynomial is going to be y equals f of a. And in fact, I'm going to write this in a nicer way. Instead of having a y there, I'm going to write this as t sub 0 of x. T, of course, for Taylor, and the 0 to remind us that this is the 0th degree Taylor polynomial. And if I wanted to be even more persnickety, I should make that 0, comma a, which tells us that it's the 0 degree polynomial centered at a. But generally speaking, the context makes it clear what we're talking about. So I'll leave that off here. All right, well, let's get rid of that stuff and move on to the first degree Taylor polynomial of f centered at a. Well, we know what a first degree polynomial is. That's a linear polynomial, like you studied in Algebra 1. But it's the first degree Taylor polynomial for f centered at a. So it's going to be some first degree polynomial, a line, a linear equation, that passes through this point and hugs the curve as closely as possible in a neighborhood of a, better than any other line that passes through this point. In other words, of all the lines that pass through that point, we want the one that is closest to this curve near a. Well, what's that going to be? Is it going to be this one? No, obviously not. Is it going to be this one? No, obviously not. It's clear what it has to be. It's going to be the tangent to the curve at that point. After all, that is the heart of differential calculus, as you learned in Calculus 1. The key geometric idea of differential calculus is that curves are locally straight. If I take a point on a curve and I zoom in with a microscope, it looks much straighter. If I zoom in further still, it looks straighter still. And on an infinitesimal scale, it's indistinguishable from a straight line. And that straight line from which it is indistinguishable, that is the tangent line. You imagine extending that. So on an infinitesimal neighborhood, this curve and this tangent line are actually indistinguishable. So of course, this is the best linear approximation to the curve in a neighborhood of a. And again, once you get further away from a in either direction, it becomes a lousy approximation. But nearby, it's very good. So the first degree Taylor polynomial for f, any old f, centered at any old point is just going to be the tangent line there, which means that we should be able to write down its equation very simply. Now, you could do this like you would do in an algebra class or something and say, well, look, I know it passes through a f of a, so I know a point on it. I know its slope. After all, its slope is f prime of a, and take that slope and take the coordinates of that point and stick it in the whatever it's called point slope form and come up with the equation. And that's fine, but it's nicer just to think about it, and I think it'll give us a little more insight into what's going on. What's the equation of that line going to be? Well, the idea is a line is anchored to the function at this point. So if I move in either direction from a, essentially my y value is going to be moving up or down from f of a. So let's just try to capture this in symbols over here. Our first degree Taylor polynomial, if we build it up bit by bit, is going to look like f of a plus some other stuff. And this other stuff is going to account for how far I've moved away from a. I don't think there's going to be enough room right here, so let me move that. Okay, that's better. So what's the other stuff? Well, let's imagine that I'm evaluating it at some nearby point x, so that this distance from a is x minus a. Now I want to think about what the slope tells me. Well, think about what slope means in general. Yeah, it's rise over run and all that, but what does it actually tell you? If I have a line and its slope is 3, that means that if I start on any point and I go over 1 unit, I have to go up 3 units to get back on the line. That means if I go over 7 units, I have to move up 7 times 3, 21 units to go back up. So the slope just tells me for every unit I run, how many units do I have to rise to get back onto the curve? Okay, so I'm looking for the equation of this tangent line. If I'm sticking x in, I want to know what's the y value on that line. Well, I started here at f of a, and I've run a certain number of units. I've run x minus a units. So how many do I have to rise? The slope tells me for every unit I run, I have to rise f prime of a units. So if I run x minus a units, I have to rise f prime of a times x minus a units. So it's going to be f of a, my base point, plus this multiplier, f prime of a times x minus a. And that is my general recipe for a first-degree Taylor polynomial. It's just a tangent line. Be sure you understand where this comes from. All right, so far so easy, and we could have done this back in Calculus 1. It gets more interesting when we forget about the first-degree Taylor polynomial and look instead at the second-degree Taylor polynomial for f centered at a, which I'll call T2. Now, what is that thing? I don't mean what's the formula for it, but what's the intuition for it? What does it signify? All right, it's a second-degree polynomial. It's a quadratic. Great. So its graph is going to be a parabola. It's a Taylor polynomial for f centered at a. So it's anchored to the thing at this point. It's going to pass through that. It's some kind of a parabola passing through that point. Which one is it going to be? It's the one that fits it best in a neighborhood of a. How are we going to find that thing? Well, we have a formula for it, and I derive it in the book. But intuitively, we know it's not going to look like that one I just drew. That's a pretty poor approximation when we get further away from a. It's probably going to look like, based on this picture, maybe something like this. That parabola hugs the curve pretty well in a neighborhood of a. And let me remind you of what this turns out to be in the book. Actually, in the book, I do everything centered at 0, so this will be a little more general. There's an exercise in the book where you extend this to this general case we're talking about now. It starts out the same, and that happens every time. Notice that the 0th degree is just this constant, which shows up here at the beginning of the first-degree polynomial. And all of that is going to show up here in the beginning of the second-degree polynomial. The lower order terms stay exactly the same. So once again, we start at f of a. That's like where the thing is anchored. We imagine we move just a little bit away from a to some value of x on either side. So if we're looking at some x, you always are thinking about, well, it's that distance, x minus a. How far away from a am I? And we have to make some adjustments for each degree of the polynomial. For the first degree, as we said, that's just going to be f prime of a, x minus a. The second order term is more interesting. It starts off just like you think, f double prime of a, the second derivative, but we have to divide it by 2 factorial. Now you might say 2 factorial, that's just 2. 2 times 1 is 2. Why don't you just write 2? Only because we want to see the pattern as it develops in higher degrees. Anyway, and that's going to be multiplied by x minus a, that crucial distance right there, squared, because this is the second degree term. And that is the general recipe for a second degree Taylor polynomial. Now this is going to probably be a fairly long video, but I don't want it to be infinitely long, so I'm not going to go through the derivation of why this works. Please see the book for that. Here I just want to continue teasing out the pattern. So let's look at the third degree Taylor polynomial approximation. That's going to be the cubic function through this point that approximates this function as best as possible, maybe something like that, who knows, in a neighborhood of a. The formula for that thing turns out to be, well, it's going to be all this stuff plus a cubic term. So it's going to look like all the previous stuff, and the third degree continues in the pattern that is already pretty clear. We take the third derivative of the function, evaluate it at a, that anchor point, divide by 3 factorial, and then we have to raise x minus a, which gives us our distance from the anchor point, to the third power. And now we've got a cubic polynomial, a third-degree polynomial. And of all third-degree polynomials that pass through that point, this is the one that most closely approximates the function near a. And now we have enough to see how the pattern continues. If we wanted the fourth degree, well, we would just tack on the fourth derivative of f evaluated at a, divide by 4 factorial, and multiply by x minus a to the 4th power, and so on and so forth. So in general, the nth degree Taylor polynomial for f centered at A. What's it going to look like? Well, the beginning is exactly as you'd expect, f of A, because it has to match the function at A, plus f prime of A x minus A, plus f double prime A over 2 factorial x minus A squared, plus, well, the pattern continues until you get all the way to the nth derivative of f divided by n factorial x minus A to the n. And that's the general pattern. And if you like sigma notation, you can write this very compactly because all of these terms follow the same pattern. You might think these first two don't, but they actually do. And what is that pattern? Let's concentrate on these ones, and then we'll just see how everything matches up. Something like the kth derivative of f evaluated at A over k factorial. We're going to let our sum go from k is 0 to n, since k is our index for the degree, times x minus A to the k. Now you might say, well, wait a second. That's fine for k is 2 and k is 3 and all the way up to n. But what about 0 and 1? Do those match up? Well, yes, because when k is 1, we're dividing this thing, the first derivative, by 1 factorial. And 1 factorial, of course, is 1, so that's why it doesn't show up here. And this kth power is 1, which, of course, we don't write there. So this one conforms to that pattern. But what about the plain old constant? It does too, because when k equals 0, well, we can think of the 0th derivative of a function as being the function itself. So this would just be f of A, which does show up here, divide by 0 factorial. You probably know, but maybe you don't, that 0 factorial is by definition 1. And it's interesting to talk about why that is so, but we don't really have time for that right now. But it is so. So when k is 0, we get the 0th derivative of A, which is f of A, divided by 0 factorial, which is 1, so that doesn't change anything. And then we have x minus A to the 0th power. Will you raise anything to the 0 power? That's just multiplying by 1. That doesn't do anything either. So even this humble f of A fits this pattern. And that's that. Now let's calculate a few concrete examples using this formula. For our first example, we'll compute the 5th degree Taylor polynomial for the exponential function centered at 0. So to visualize this, here's our good old friend, the exponential function, and we want to imagine a 5th degree polynomial that hugs this thing very closely, at least in the neighborhood of 0. And here is the recipe for it. So I'll begin my solution, as you might say, on an exam. The polynomial we seek is, now you don't have this written on the exam, so we have to reproduce it, but with the specifics in mind. So since we're centering it at 0, we know that the polynomial will begin with the constant term f of 0, corresponding to our anchor point right there. Then the next term, of course, will be f prime of 0 times, well, our general term is x minus A, but A is 0 in this case, so x minus 0 just becomes x. Then we get f double prime of 0 over 2 factorial x minus A, but again, that's just plain old x in this case squared, since A is 0. And of course, it's the same story for the 3rd order term, as well as the last two. We stop at the 5th order because we are looking for a 5th degree Taylor polynomial. So now all we have to do is fill in pieces for this specific function. We've already taken care of the a's. Now we just have to fill in these values right here, the values of the function and its derivatives at 0. Well, that's easy in this case. Since f of x is the exponential function, the defining property of the exponential function is that it's equal to its own derivative. So its derivative is also e to the x, and its second derivative is e to the x, and its third, and its fourth, and its fifth, and so on and so forth. So we know that all of those derivatives are equal, and they are all equal to e to the x. That's important to us because we have to evaluate all those derivatives and the original function at 0. So f of 0 is the same as f prime of 0, since f and f prime are the same, which is the same as f double prime, triple prime, quadruple prime, and quintuple prime of 0. And when we evaluate them all at 0, well, we get e to the 0, which of course is 1. That means all of these various expressions up here can be replaced by 1s. So the Taylor polynomial we seek is this guy right here. And we're done. Of course, if you like, you could change these into the actual numbers. That's a 2, that's a 6, that's a 24, and that's 120. But let's leave it like this because it shows the pattern so clearly. This pattern is very famous and you should know it. You should have it memorized. Obviously, it continues this way as far as you want to go. If you wanted the 92nd degree Taylor polynomial for e to the x, well, it would continue plus x to the 6th over 6 factorial plus blah, 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 all the way to plus x to the 92nd over 92 factorial. a famous pattern. Know the beginning. We'll use it frequently in this class. I want to show you what it looks like on a graphing program. So let me hasten over to GeoGebra.
Okay, here is the exponential function, and I want to show you the first few Taylor polynomials for it, centered at 0. I've got that dot on there at 0, 1, where they will all pass through. So let's start with the 0th degree polynomial. No surprise, that's just a straight line through that point. The first degree polynomial, we said, is going to be the tangent line to the curve at that point. And here it is. Now, of course, it fits the curve exactly at the point, and it looks pretty good nearby 0. But even by the time you get to 1 or minus 1, it's noticeably different from the curve. Well, anyway, let's get rid of that and look at the second degree polynomial. That's much nicer. That's the best fit parabola. It hugs the curve pretty nicely, almost all the way up to 1 and minus 1. Compare the first degree and the second degree, you can see how much better a fit the second degree is than the first. Okay, well, what about the third degree? The third degree is going to be the cubic that fits the curve best near that point. Ooh, that's even better. Look at that. Let's go for the fourth degree. The fourth degree is looking better still. And finally, the fifth degree polynomial. There is the fifth degree Taylor polynomial. I will remove the other ones, and that is the one that we generated. It really is almost indistinguishable from the curve, quite some ways on the right and a good ways on the left too. But let's get rid of that and take this even further. What I have done is cooked up a little movie here, a little animation, where we start with the 0th degree Taylor polynomial, and we're going to increase it 1 degree at a time all the way up to 20. And you can see how it hugs the curve better and better. So let's roll the film, and we'll count off the degrees. Ready? 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And there is the 20th degree Taylor polynomial. And a natural question is, if we keep increasing the degree, will it keep creeping down the x-axis, hugging that long asymptotic tail all the way to infinity? In fact, it will, but that's not something we can prove right now. But still, it's interesting to see that happening on the screen. And I encourage you to get on GeoGebra yourself and play around with it. It has a nice command for Taylor polynomials. But let's get back to our regularly scheduled program.
So to summarize, the exponential function can be approximated by a polynomial of this form. The approximation gets better and better the further you go out. This is a lousy approximation. This, the linear one, is not too bad when you're very close to 0. This one is better still. It allows you to get a little further away from 0. This one is even better, and so on and so forth. This being calculus, you can probably imagine what's already going to happen. We're eventually going to take a limit as n goes to infinity, and we have not just an ordinary polynomial, but a polynomial of infinitely many terms. That will be called not just a Taylor polynomial, but a Taylor series. But more on that later. For now, be sure you know this and you understand where it comes from. Let's move on to another example. Let's find the 4th degree Taylor polynomial for this function, 1 over 1 minus x, centered at 0. You might think, oh, that's a funny looking function. Well, as you will see very soon, this turns out to be a very important function, and you will soon understand why the Taylor expansion for this function is very, very, very important. You'll understand this when we get to so-called geometric series in a couple of days. But for now, let's just think about this before we start bashing out the Taylor expansion. What does the graph of this thing look like? Don't turn to your calculator or your favorite graphing program. Just think it through. Is there a function very close to this whose graph you know? Well, yes, everybody knows what the graph of y equals 1 over x looks like. It looks something like this with those asymptotes. Well, think about the basic transformations you learned probably in a pre-calculus class. What happens if I substitute in place of x, x minus 1? What does that do to a graph if everywhere you have an x, you stick in x minus 1? Well, I hope you remember. It shifts the graph over to the right by 1 unit. So instead of this point here, which was at 1, 1, it would move over here to 2, 1. And we would have something like this coming down with an asymptote there. And instead of having this asymptote, we would end up with one like that. Okay, but I hear you cry, hey, wait a second, this is 1 minus x, not x minus 1. You made a mistake. Well, I only did that so that I could get to this thing. How do I get from this to this? Well, of course, I just multiply by minus 1. If I multiply the whole thing by minus 1, it turns into 1 over 1 minus x, which is the thing I'm actually trying to match. Okay, so this algebraic transformation, multiplying the right-hand side of a function by -1, what does that do to its graph? That's a reflection. You're flipping everything over the horizontal axis. So the blue gets flipped into the red, and now I have the graph of the function that I wanted. So here it is. That's the graph of the function whose Taylor polynomials we're trying to find. So we are looking for some function that will hug it very closely in that neighborhood of 0. Okay, let's get to the actual calculation. We didn't need this stuff to get the Taylor polynomial, but it helps us visualize what's going on a little bit. So, our solution. We're looking for the 4th degree Taylor polynomial. That means we need this function and its first 4 derivatives. And then we're going to have to evaluate those derivatives at 0. And those are all going to show up in our general recipe. So let's start by writing down the function and its first 4 derivatives. Here's f of x, and it's going to be easier to take those derivatives if I write that with a negative exponent instead of a fraction. And when we start taking derivatives, we'll notice a nice pattern develop. Here we get minus 1 minus x to the -2, but don't forget the chain rule. I have to take the derivative of this stuff on the inside, which gives me another -1. So that's going to get rid of that negative. Let's move on to the second derivative. We're going to get -2, 1 minus x to the -3, but again, don't forget the chain rule, which clears out that negative. And again, for the third derivative. Now, when I take the derivative here, I'm going to get a -6, but I am going to leave that as -3 times 2. It's not because I've forgotten how to multiply, but rather because we're going to see an important pattern develop here. Oh, but don't forget the chain rule. So again, that negative disappears. Now when we take that fourth derivative, well, the -4 comes and multiplies with those. The new exponent becomes -5. Chain rule gives us the -1, which is going to nix the negative we picked up originally. And we end up with this stuff. And now you can see how the pattern develops. That's as far as we need to go here because I asked you for a 4th degree Taylor polynomial. But you can see what the 5th derivative is going to be. 5 times 4 times 3 times 2, which is better known as 5 factorial. Something nice is about to happen. But first, we don't just want the derivatives of the function, we have to evaluate at the point where we have centered our polynomial, a, which in this case is 0. So, all these guys lead to expressions for the value of the function and its first 4 derivatives at 0. When I pop 0 into all of these expressions, I get 1, and here I get another 1, and here we get 2 times another 1, so that's going to be 2, and here I get 3 times 2 times another 1, so that's going to be 3 times 2, and here I get 4 times 3 times 2 times another 1, so that's 4 times 3 times 2, or if you like, that's 4 factorial, and 3 factorial, and 2 factorial. And if you really like, that's 1 factorial and 0 factorial, but I'm not going to bother. And because of these factorials appearing, we're going to get some wonderful cancellation. So the Taylor polynomial we seek is, well, we know how the general expression always begins. F of 0, the value of the function at the center point, plus f prime of 0 x, plus f double prime of 0 over 2 factorial x squared, plus triple prime over 3 factorial x cubed, plus quadruple prime over 4 factorial x to the 4th. And now we just need to fill in all of these values. F of 0, we said, is going to be 1, so I'll put that in. F prime of 0 is also going to be 1, so this just becomes x. This guy, f double prime of 0, that's 2 factorial, but it's being divided by 2 factorial, so all of that becomes 1, and that constant disappears. And what about this one? Well, I've got f triple prime. But that's 3 factorial, and it's getting divided by 3 factorial. So that stuff, that coefficient, all becomes 1. It's gone. And the same story right here. Well, that's extremely simple, but these vast spaces are making me nervous, so let me put them together. And voila, we have a very simple 4th degree polynomial. All the coefficients are 1. We will be seeing more of expressions like this. Let me show you also what it looks like on GeoGebra.
Here I have the graph of 1 over 1 minus x plotted as promised, and I will show you the 4th degree Taylor polynomial for it, centered at 0, that we just constructed. Here it is. That's quite a good fit in a neighborhood of 0. And in case you were curious, here were some of the lower order approximations. There's the 3rd, there's the 2nd degree, There's the first, which of course is just the tangent line, and there's the 0th, which nobody really cares about, so I'll get rid of it. Now, one thing that's worth noting here is that even when we get to our 4th degree approximation, the polynomial pulls away from the curve really rapidly before we get to x equals -1. And that continues to happen even if we take very high order Taylor polynomials. For example, here is the 20th degree Taylor polynomial. And while it is very good near 0, you can see that it still tears away from the curve itself as it approaches -1. And this is very much like the example I gave in the book, where we were looking at the function 1/1 plus x squared, where I said it was as if there were laser tripwires that came with the function here at -1 and 1 that ensured that as soon as the curve passes through those tripwires, the polynomial can no longer approximate it. What that is all about is something that we will discover as we go further and further into the chapter. For now, just let it be a mystery and appreciate the fact that you've been able to construct this polynomial that fits the function so well. And of course, you would have no trouble constructing the 20th either. That would just be 1 plus x squared plus x cubed plus x to the 4th plus so on and so forth up to x to the 20th. Let's get back to the blackboard.
So that's that. That was another sufficiently important result that you should have it memorized. Let me summarize it here. The function 1/1 minus x is approximately equal to this stuff. 1 plus x squared plus x cubed all the way up to x to the n. And of course, this gets better and better the more terms you include, at least for values of x near 0. Much, much more on this to come. In the limiting case, where we go to infinity and we have infinitely many terms, this is going to become what we know as a geometric series. More on that very soon. But for now, get the pattern in your head. For our third and final example, I'm going to do one that is not something you should memorize. It is really disgusting, and I deliberately want to give you a nasty one, both to just see how that unfolds, and also to review a little trigonometry. There's a lot of trigonometry in this course, and if you don't know trigonometry well, you need to get it in your head and get it there well and soon. So I'll review a bit as we go, but the work of learning trigonometry, if you don't know it already, is something you're going to need to do. Fortunately, it's a really self-contained subject, so it's not hard to learn it, even if you didn't learn it well the first time. Anyway, what I want to do in this example is to find the 3rd degree Taylor polynomial for cosecant x, centered at 3 pi over 4. I'm going to need a fair amount of room, so let me move this up here. Okay, that's a bit better. Now, from a purely conceptual point of view, there's nothing more complicated about this problem than the previous two, right? We just have our function, we need to take its first 3 derivatives, evaluate those first 3 derivatives at 3 pi over 4, stick the results in the formula, and we're done. There's nothing deep here. But I want to take some extra time just to dwell, as I said, as a reminder of trigonometry. So first of all, what is cosecant? It's not a trig function you meet every day. It's one of the 3 reciprocal trig functions. It's the reciprocal of the sine function. I always remember those reciprocal functions are heterosexual. Cosecant with a C goes with sine with an S. Secant with an S goes with cosine with a C. And of course, cotangent goes with tangent with a T. But anyway, what does the graph of cosecant look like? We don't strictly need it to come up with this Taylor polynomial, but let's not be so utilitarian. Let's make sure you know some trigonometry. No one has the graph of cosecant memorized. You might know the vague shape of it, but there's no need to memorize it. 1, because cosecant doesn't come up all that often. And 2, if you understand what the sine wave looks like, then of course you can come up with it because cosecant is just its reciprocal. So let's think our way through that. Here's the graph of sine. Everybody knows what it looks like. Well, cosecant is the reciprocal of sine. So how do you find the cosecant of a value? Well, you take its sine, and then you take the reciprocal of the result. So for example, if you're looking at this point right here at pi over 2, the sine is 1, so the cosecant is the reciprocal of 1, which is still 1. So if we're going to put cosecant in blue, we'd have a point right there. If we took a point over here, like say pi over 6, 30 degrees, where sine is a half, cosecant is the reciprocal of that half. In other words, it's 2. So we'd have a point over here. And in general, when you take the reciprocal of numbers between 0 and 1, of course, you get numbers from 1 to infinity, right? You take the reciprocal of something tiny, like 1 over 10, and you get 10. Take the reciprocal of something really tiny, like 1 over a million, and you get a million. So I'm going to get this asymptote up here, and the same thing is going to happen here. I'm going to get an asymptote there, and my graph is going to look like this. And the same thing is going to happen over here, except everything's going to be negative, and so on and so forth. So this blue stuff is going to be our graph of y equals cosecant x. Good. And in this problem, we're thinking about a third-degree Taylor polynomial for cosecant centered at 3 pi over 4. So that looks like it would be somewhere around here. So we're going to look for some sort of polynomial that hugs this thing really closely, at least in a neighborhood of 3 pi over 4. Okay, at least now we have a picture in our head what we are aiming at, and we have reviewed some trigonometry on the way. Let's start working on our actual solution. For that, we're going to need the first few derivatives of cosecant, and we'll need to review a few things there too. So, if f of x is cosecant x, what's f prime of x? Hopefully you have that memorized, but if you don't, or you need your memory jogged a little bit, just remember how the derivatives of the trig functions work. They're really easy. There's only 6 functions, and they follow specific patterns. Hopefully you have those in your head, and you did not have a very nice teacher who let you bring a page of notes to a test or something like that. It turns out not to be so nice in the long run. But either way, let's review quickly. So here are our 6 trig functions, the 3 main ones, sine, cosine, tangent, and the 3 reciprocal trig functions, cotangent, secant, and cosecant. Let's think about their derivatives. Everybody knows the first 2, of course, and the only thing I'll observe here is that the derivative of cosine is negative sine. That negative is an important part of the pattern that makes these things so easy to memorize. And tangent is the other one that everyone knows. Though it might be a little shaky, it should not be. It's a very important one. Derivative of tangent is secant squared. I'm assuming if you've made it this far in calculus, those pose no trouble for you. Now really, of these 3, the only one you really need to commit to memory is secant. And you may or may not remember that one. If you don't, it's secant tangent. Why do I say that's the only one you have to have in memory? Oh, and by the way, how do we come up with that derivative? Well, that's easy. Secant is 1 over cosine. Then you can crank out the derivative using the quotient rule. And if you do that, and that's a good exercise, you'll come up with that. Okay, but as I said, this is the only one you really need to memorize. Derivative of secant is secant tangent. Why don't you have to memorize anything special for cotangent and cosecant? Because they're both co-functions. Cotangent is the cofunction of tangent, and cosecant is the cofunction of secant. And the derivatives of the 3 cofunctions, cosine, cotangent, and cosecant, are all almost exactly like the functions with which they're paired. For example, derivative of cosine is like the derivative of sine. Take the derivative of sine and you get cosine. Take the derivative of cosine and you get, well, of course, instead of cosine, you get the cofunction, sine, and you pick up a negative. You pick up a negative every time you take the derivative of a cofunction. You pick up a negative and you switch all the functions to their cofunctions. So for example, derivative of tangent is secant squared, so derivative of cotangent turns out to be, well, you get that negative because you're taking the derivative of that cofunction, and instead of secant squared, you get cosecant squared. That's it. Similarly, what about the derivative of cosecant? Well, you end up with a negative because you're taking the derivative of one of those 3 co-functions. And then you think, well, what's the derivative of secant? Well, that's secant tangent. So the derivative of cosecant is the same thing, but with the co-functions. Cosecant, cotangent. And that's it. Those are the derivatives of the trig functions. Very simple patterns. Anyway, let's get back to our task at hand. What's the derivative of cosecant? Well, we just said it's a cofunction, so we get a minus. And it's like the derivative of secant, which is secant tangent, except we get the cofunctions, cosecant, cotangent. All right, now for the second derivative. Ooh, that looks kind of ugly. It is kind of ugly, and it would make a great problem in Calculus 1. So let's review. We're going to need the product rule here. I'm going to take this and just reserve it outside. So what's the derivative of this stuff? Well, we need the product rule. Derivative of this times this plus this times derivative of that. So what's the derivative of cosecant? Well, we've said it like 3 times now. We get a minus, and then it's like secant, but we get the cofunctions. So cosecant, cotangent. But I have to multiply by cotangent itself. So that's going to give me a second factor of cotangent. Second term in the product rule, the cosecant just sits there, and now I need the derivative of cotangent. What's that? Well, I get a minus, and it's like the derivative of tangent, but it's not secant squared, it's cosecant squared. So I get this. Oh, that's nice, that simplifies. So this all becomes this, and now I'll distribute that negative that was waiting in the wings. That doesn't look too bad. Well, at least not as bad as it did. But can I clean it up a little more? Yes, I can, if we have a decent grasp of trigonometry and some basic trig identities. Because what have I got here? I've got some cosecant stuff, 1 copy here and 3 here. And then I've got some cotangent stuff. And in fact, I've got 2 copies of cotangent, cotangent squared. And I might remember, oh yeah, there's an identity involving squares of cotangent and squares of cosecant. That means I should be able to turn this cotangent squared stuff into cosecant squared stuff. And then everything will be in terms of cosecant, and that'll be a little nicer. But damn it, what is that identity? Well, you probably don't know it off the top of your head. I certainly don't. But you should be able to get to it in about 2 seconds from something you certainly do know. It's one of those Pythagorean identities. So let's come over here in reminiscence land again. Everybody knows the main Pythagorean identity, cosine squared plus sine squared is 1. And everybody should know that there are 2 other identities that you can extract from that just by dividing both sides by the appropriate thing. The more famous of the 2 other ones you get if you divide both sides by cosine squared, because then you end up with, on the left-hand side, cosine squared divided by cosine squared is 1, plus sine squared divided by cosine squared is tangent squared by a famous identity that everyone knows. Sine over cosine is tangent. And 1 divided by cosine squared is, of course, secant squared, by definition of secant. This one often gets used in doing integrals and things like that. It has a somewhat less famous cousin, which you get if you divide both sides by sine squared. If you do that, then you get cosine squared over sine squared, which is cotangent squared, plus sine squared over sine squared, which is 1 over sine squared, which is cosecant squared. And these are our 2 alternate forms of the Pythagorean identity. And we could use that one here to simplify cotangent squared. You don't have to, but it'll make it easier to take the next derivative. So let's do it. If we do that, we would get cosecant x times, instead of this cotangent squared x, I'm going to use it in this identity and substitute in and say that cotangent squared is cosecant squared minus 1. So I'll pop that in here. And of course, I still have my cosecant cubed. Now, once I distribute this and collect like terms, I've got 2 cosecant cubed minus cosecant. And now everything is in terms of cosecant x, which is a little nicer. So to give myself a little more room, I'm going to clear out these intermediate stages. And now I've got my second derivative. And we need one more derivative because we're going for the 3rd degree Taylor polynomial. So the 3rd derivative is going to be, well, let's see. First, this 3 is going to come down and combine with the 2, and we will get 6 cosecant squared x. But don't forget the chain rule. We still have to take the derivative of the inner function cosecant x. And as we've said, we're going to get a negative when we do that in the beginning. Derivative of secant is secant tangent, so this is going to be cosecant cotangent, like that. And we still have to take the derivative of our second term. Well, we're subtracting that derivative, but when we take the derivative of cosecant, as we said, we're going to get a negative, so that'll turn that into a positive, and derivative of cosecant is like secant, which is secant tangent, but it is cosecant cotangent once again. And now let's clean that up because that minus factor in the middle is disgusting. That's better. Oh, and actually we have 2 copies of cosecant here and 1 here, so let's combine those, and that's much better. Let's leave it there. So now we've got all of our derivatives, but we still need to evaluate them at 3 pi over 4, which is going to lead us to a little more trig review, which we will do down here on the other side of the blue line as usual. But remember the goal. We are trying to evaluate each of these things at 3 pi over 4. Well, what's that going to involve? We're going to stick 3 pi over 4 into each one of these 4 functions. To do that, we're going to need to know the cosecant of 3 pi over 4, and we're going to need to know the cotangent of 3 pi over 4. And if we know those 2 things, we can evaluate all these things very easily. But do we know those things? Hopefully you can come up with them without relying on a calculator. You certainly should be able to, not because it's so important to know what cosecant of 3 pi over 4 is, but it is very, very important to know all those different interlocking trigonometric relationships that you use to come up with those. And every time you review those in your mind, it helps reinforce them. So let's do a little of that down here. What's cosecant of 3 pi over 4? Well, what does that mean? That's 1 over sine of 3 pi over 4. That's the definition of cosecant. Can you come up with this? I hope so. But let's review just to make sure. We have to think, what does sine of 3 pi over 4 mean? It's just chasing definitions around. Well, that's defined on the unit circle. So 3 pi over 4, that's 3/4 of a half turn. So it's that angle right there. And the sine of that is, of course, the y coordinate of that point. Well, nobody knows the values on this quadrant. we just learn the values on this quadrant and then use symmetry. The y-coordinate of that point is the exact same as the y-coordinate of that point at the angle pi over 4. So the sine of 3 pi over 4 is the same as the sine of pi over 4. And that is something that, of course, everyone has memorized. That's 1 over root 2. So when we take the reciprocal, we just get plain old root 2. Well, that's not bad at all. That means when I substitute these 3 pi over 4s in, I'm going to get a lot of square root of 2's over here. All right, but we are still going to need to evaluate all these various cotangents at 3 pi over 4 as well. So we need cotangent of 3 pi over 4. How do we get that? What does it mean? That's, by definition, the reciprocal of tangent of 3 pi over 4. Well, what's that? Well, there are lots of ways of coming up with that. I think the nicest one is to know the interpretation of tangent on the unit circle, that the tangent of any angle is the slope of that radius right there. So if I go 3 pi over 4, what's the slope of that radius right there? Well, of course, that's minus 1. So that's 1 over minus 1, which is minus 1. That's even simpler than the square root of 2 we had before. Anyway, lots of good stuff in trigonometry, but we've got the two values we need. Now let's come back over here and plug these things in. When we stick 3 pi over 4 into the original function, we get cosecant of that, which we have said is going to be root 2. When we stick it into the derivative, we get negative this times this. Well, their product is minus root 2, so the negative of that is plus root 2, yet again. Second derivative, we stick that in. This one's going to take a little more care. We're going to get 2 times the cube of the cosecant. That's the cube of square root of 2, which is 2 root 2, minus the cosecant, which is another root 2. Well, let's combine all that. That's 4 root 2 minus root 2, so that all becomes 3 copies of root 2. And finally, when I pop it into the third derivative, we're going to get minus 6. So minus 6 times the cube of the cosecant. Well, that's 2 root 2 times the cotangent, which is minus 1, plus the cosecant, which is root 2, times the cotangent, which is minus 1. And when we sort this mess out, let's see, we get 12 root 2 minus 1 root 2, so that is going to be 11 times the square root of 2. Hooray! And now we have all of our values, and we can just drop things into the formula for the Taylor polynomial, and we will have the Taylor polynomial we need. So let me clear out the trig review space. The Taylor polynomial we seek is, how does it begin? As always, the value of the function itself at the point where we're centering it. And then we have the derivative there times x minus, well, we're doing everything in terms of 3 pi over 4, so we're going to have that. And then we get our next term with the second derivative, and we're dividing by 2 factorial. And of course, we've got a square on that difference, x minus 3 pi over 4. And then finally, the last one, the third derivative, dividing by 3 factorial, and the third power here, which brings us all the way up to the degree that we wanted. That's the general form for a third-degree Taylor polynomial for any function f evaluated at 3.4. But to get it for our function f, we just have to substitute in the specific values of the function and its various derivatives there. So let's do that. This guy, we said, is just going to be the square root of 2. This guy, the first derivative, is also going to be the square root of 2. This fella up here is 3 root 2, but we're dividing by 2 factorial, which is 2, so we end up with 3 root 2 over 2 as that coefficient. And finally, for the third degree coefficient, well, the top, the third derivative, is 11 root 2, and we're dividing by 3 factorial, which is 6. So that is going to be 11 root 2 over 6. And at long last, we are done. That is our Taylor polynomial. And to celebrate our achievement, let's go ahead and graph that guy on GeoGebra 2 to see what it looks like.
And here it is, the graph of cosecant, looking just like we said it would. We came up, after some laborious calculations, with the third degree Taylor polynomial for cosecant centered at 3 pi over 4. And if we plot that third degree polynomial on GeoGebra, it looks like this. Pretty good, though again only in a neighborhood of that point where the polynomial is centered. Still, it's better than the second degree polynomial, or of course the first. If we went further, braving those horrible calculations, or as I did, just letting GeoGebra do them for me, I get my fourth degree approximation, which looks a little better. And I did one more, I did an 8th degree approximation, which looks better still. If you get much higher than that, the calculations get so gory that the computer starts to freeze up, so I stopped there. But here too, the approximation looks great in a neighborhood of 3 pi over 4, but everything seems to go out the window when you get a little lower than x equals 2. And in fact, the same sort of story happens that happened with y equals 1 over 1 minus x, or that example I gave in the textbook. We have these secret tripwires that seem to destroy the Taylor polynomial's ability to mimic the function once the function crosses over them. Not every function has such tripwires. The exponential function we looked at before does not. By raising the degree higher and higher and higher, the polynomials hug the graph of the function further and further and further away, all the way out to infinity. That happens with some functions, it doesn't with others. Let it be a mystery for now. We will discover the reasons later. But at any rate, this has been a long video. Most of them should not be this long, but I hope it has helped, both with your understanding of Taylor polynomials and as a side benefit of trigonometry too. See you next time.